Hello, this is Mr. Gilmore with the 9.4, the Inscribed Angle Theorem lesson. Today we're going to introduce a new definition of what an inscribed angle is and its relationship that it holds with the arc that it cuts. Let's go ahead and dive into that definition. So an inscribed angle by definition is an angle whose sides are chords. If you take a look at the diagram down below where we have the two segments AB and AC, by definition they are both chords and also they share that common vertex A, which then means, again by definition, we have ourselves an inscribed angle. Now, another definition for the inscribed angle is that it's an angle such that its vertex is a point on the circle. So again, our diagram, we have angle BAC is what we call an inscribed angle. Now, we've seen angles that have appeared on the interior of our circle before, and there are central angles where the vertex of the angle is at the center of a circle. So now imagine taking that vertex, which is at the center, and dragging it to be a point on the circle. Notice again then that the angle, the inscribed angle here is also cutting an arc, very much like the central angle cut an arc. We're going to take a look at that relationship that the inscribed angle has in terms of its measure with the measure of the arc that it cuts. Now, we are going to have to redefine the word cut because the way we defined it first was based on the central angle. Well, now we have to open that up because now it also involves our inscribed angles. So when we talk about the arc cut, we're going to say that the arc cut by an angle is the arc in its interior. So think about then as we extend out the rays that are produced from this angle here, the ray from A to B and the ray from A to C, notice that they are cutting this arc that is on the interior of the mouth of that angle, which means that's how we're going to redefine this word cut as we move away from specifically the central angle and now introducing really any sort of angle, such as the inscribed angle, to find that there is an arc also cut by that inscribed angle. So in the diagram below, we would say that arc BC is cut by the angle BAC. Now on to our inscribed angle theorem. See, what we're going to look at is that there is a relationship between the measure of that inscribed angle in terms of its relationship with the arc that it cuts. So here's what we're going to prove, that the measure of an inscribed angle is actually half the measure of the arc that it cuts. In other words, if we take a look at our diagram specifically, we'd say that the measure of angle, the inscribed angle, BAC, is equal to half the measure of the arc BC. So we could play around with some numbers. Essentially, let's say that the angle here, BAC, is 30 degrees. Well, that means that the arc that it cuts is 60 degrees. It's going to be half of that. And of course, I can do, let's say that the arc that is cutting here, the measure of the arc is 100 degrees, then the angle of this inscribed angle is going to be half of that, right? 50 degrees. And so we're going to prove this specifically for the inscribed angle theorem, that the measure of the arc is going to be, the measure of the central inscribed angle is half the measure of the arc that it cuts. Now, as it turns out, the inscribed angle theorem actually has three cases to it. And we're going to start here with case one. Then we'll see then following this will be the proof of case one, and then we'll take a look at the other two cases. So the breakdown of this, we take a look at really where the position of the sides of our angle fall. And we're going to take a look at case one, where where one side of our inscribed angle happens to be a diameter. It passes through the center of our circle. So if you take a look at our diagram below, we've got circle A with our inscribed angle BCD. However, we're also saying this is a special case, case one, such that the side of our angle passes through the center. In other words, BC, the side of our inscribed angle, passes through point A, the center of our circle. Now, our goal is to still prove that the measure of the inscribed angle is half the measure of the arc it cuts. So in this case, we're going to prove that the measure of angle BCD is equal to half the measure of the arc it cuts, the measure of arc BD. Let's dive into this proof. So the proof of case one, a bit extensive just because of the level of work we have to introduce and the relationships that we're going to be building between angle measures and arc measures. So we have the same given. We've got our same diagram. Let's again prove that the measure of angle BCD is equal to half the measure of the arc BD. So we start with our given, right? Step one, got our given. Circle A, inscribed angle BCD. We have our chord BC as a diameter. Now, the first step after that is we're going to make a construction. We're going to connect point A to point D. And by doing that, we form ourselves another radii that appears in this circle. And what we're going to use that radius we've just constructed is compare it to another radius, and we can claim then the length of that radius we just constructed, AD, is equal to another radius, AC. C. So take a look there. AD is equal to AC by definition of radius. What happens there is we actually have formed ourselves an isosceles triangle. ADC is isosceles with side AD and AC equal. So the next thing we can do is we can claim that the angles opposite of those equal sides are also themselves equal by ITT. So angle BCD is in fact equal to angle ACD. Now notice that I refer to that angle ACD, which is really the angle focused on, I refer to that as the angle BCD. Now, there's something also going on with those two angles, BCD and ADC. If you take a look, there's this angle that actually formed when we constructed our radius, BAD, angle BAD. Notice anything special about that angle? There's actually two things going on. The first thing is angle BAD is an exterior angle to the triangle ADC. If we extend out our side AC through point A to point B, we've got ourselves an exterior angle. And we proved way back in chapter 4 that there's a relationship that that exterior angle has with its remote angles. As it turns out, the two angles we just found equal, BCD and ADC, those are the exterior angles, remote angles. So in step 5, we use what we call the triangle exterior angle equality that says the sum of the remote angles is equal to the measure of their exterior, which means the sum of BCD, angle BCD, and the measure of angle ADC, if we add those two together, it equals this exterior angle BAD. Well, there's something also important going on about that exterior angle BAD. It's more than just an exterior angle, it's a central angle as well, which means it's cutting the arc it's cutting arc BD. And that's going to be our main relationship that we're going to build between our inscribed angle, we're going to build it to our central angle, and that central angle is going to build it into the arc that it cuts, which happens to be the same arc that the inscribed angle is cutting. So take a look at step 6. We know that our central angle, angle BAD, is actually cutting the arc BD, and those arc that the measure of the central angle and the measure of the arc are equal in measure by our definition of arc measure. And now for some substitution, we're actually going to take we're going to go back here to step 5. Okay, here in step 5, and we're going to take what we have here in step 5 and do quite a bit of replacement. So we're going to take first, we'll leave our first term BCD. So take a look here at step 5 as it's going to lead us here into the first statement here in step 7. So we take our first term, leave it the same. Measure of angle BCD, we carry that with us. But the measure of angle ADC, we know it's equal to the measure of angle of BCD because of the isosceles triangle theorem, which means let's take our angle ADC and replace with angle BCD, which means we got the sum of two BCDs there. And also at the same time, take the angle BAD, which is the exterior angle, and set it equal to the measure of the arc it cuts, which is just the measure of arc of BD. Now simplifying, also in step 7, we've got measure of angle BCD plus measure of angle BCD is really 2 times the measure of angle BCD is now equal to the measure of arc BD, and then by a simple step of division, by dividing both sides by 2, we get our last statement. The measure of our angle BCD is equal to half the measure of arc BD. And there we have it. We've proved our first case of the inscribed angle theorem. So by the inscribed angle theorem, case 1, we know that if the side of our inscribed angle passes to the center, then we do know that it cuts, it's going to be the measure of that inscribed angle is half the measure of the arc that it cuts. Now, there are 2 other cases. Let's take a look at case 2 of the inscribed angle theorem. This is where we have the 2 sides of our inscribed angle such that the center of our circle passes on the interior of those 2 sides. So let's take a look at our diagram below. Again, we have circle A. Again, we have inscribed angle BCD. This time, though, the point A, which is our center, is passing on the interior of angle BCD. We don't have one of the sides actually passing through the center. We actually have the center being on the interior of these two sides. Once again, we're going to prove that the measure of angle BCD is equal to the measure of the arc BD, that the measure of the inscribed angle is half the measure of the arc that it cuts. Let's take a look at this proof together. So now we'll move on to case 2. Same setup as before, we just saw on the last slide. Again, we're going to prove the measure of angle BCD is equal to half the measure of BD, but we have a better tool for us to use in this case. We have our tool of the inscribed angle theorem, case 1. Let's see how we can actually take that and use that to our advantage. See, the very first thing we're going to do right off the bat, once we've got this diagram set up and are given in the step 1, we're going to actually construct a diameter from point C through point A to the other side, and we'll call that opposite point there that it intersects the opposite side of the circle at point Z. Okay, we'll call that point Z. So again, we're going to construct this diameter CZ. What then happens is you notice that there's this inscribed angle BCZ that has a side as a diameter, which means we can look at the opposite arc there and say, hey, look, an inscribed angle. BCZ is actually half the measure of the arc it cuts, BZ. Why do I know that? That's the inscribed angle theorem, case 1. And again, I have a second inscribed angle, DCZ. It also is cutting an arc DZ, and we know that the measure of the inscribed angle, if one of the sides passes the center, which it does, the measure of the inscribed angle is half the measure of the arc it cuts. Hey, take a look at that. That means the measure of angle DCZ is half the measure of the arc it cuts DZ. That's again the inscribed angle theorem, case 1. So we can take those equal angles on those equal half arcs, and we can add equals to equals. So we take a look here at step 4. I'm adding the measure of our inscribed angle BCZ to the measure of the inscribed angle DCZ, and I'm also adding half the measure of arc BC to half the measure of arc DZ, because I know equals added equals are equal. Well, now I can put those together, because the sum of those two inscribed angles are equal to the whole angle BCD, and the sum of those two arcs are equal to the whole arc BD, which means I'm using in step 5 both the angle addition postulate and the arc addition theorem. And so there we have it. There's our proof of case 2. We arrived to the conclusion again that if the center of the circle is passing on the interior of our inscribed angle, then it is true that the measure of the inscribed angle is half the measure of the arc that it cuts. Now on to our last case, case 3. In case 3, we now have the center of a circle in its third option, which is to be on the outside, right, or in the exterior of the inscribed angle. So in our diagram, we have angle BCD again, the circle A, or center A, which is now on the exterior of it. And once again, we're going to prove that the measure of the inscribed angle BCD is equal to half the measure of the arc it cuts. Let's dive into then case 3's proof. Case 3 proof is almost the same as case 2's proof. We're going to take full advantage of the inscribed angle theorem case 1. However, towards the very end, we have to take a different approach. So the very first thing we do right off the bat, once we've got our diagram, our given and proof statement set up, and we've got our statement 1 listed, which is our given, I'm going to construct again that same diameter as before, passing the center of our circle, point A, and let's call the opposite side Z, or opposite point there, Z. So step 3 is identical to what we saw before. We have these two inscribed angles. However, take a look here. The inscribed angles such that they are passing the center is this entire angle BCZ, and then part of that angle, part of that angle DCZ. So those two angles both have a side as a diameter. So again, I can use then the inscribed angle theorem case 1, but notice that the arcs that they're cutting are the entire arc here and this partial arc. Okay, this partial arc from D to Z. But we are focused on our main portion of the arc here, which is our BD, and this inscribed angle here, BCD. So we have to figure out how to relate those together. Well, again, the measure of angle BCZ, which is the entire angle, equals the measure of that entire arc, half the measure of that entire arc, measure of arc BZ. The measure of angle DCZ is half the measure of that arc DZ. That's, again, in inscribed angle theorem case 1. Thus, we can actually, if we want the part of the whole, we can take away the other part. So we're actually doing subtraction here. We're taking these equal things and taking equals away from equals, and what that's going to give us are equal remainders. And that's what we want. So if we take BCZ, the whole thing, and subtract off the part, we're left then with the other part of the angle, measure of angle BCD, and then we have the whole arc BZ. We take off the part of the arc DZ, and we're left within the remaining part of the arc BD. And so thus the measure of the angle BCD is equal to half the measure of the arc BD, again using angle addition postulate and our arc addition theorem. And there we have it, the proof of case 3. So basically then, what we have here with inscribed angle theorem is all three cases come together to form the one conditional, the one theorem, inscribed angle theorem. And so now we have all three cases proven. No matter where we find ourselves encountering an inscribed angle theorem or inscribed angle, we can apply the IAT, the inscribed angle theorem, to that given angle, because we know it will work in all three of the possible cases that an inscribed angle that is formed. So we don't have to actually refer to them as case 1, case 2, or case 3. Each of those come together to form the complete version of our inscribed angle theorem, or the IAT. Now let's do a little bit of reflection on these three cases that we actually just proved. See, number 1 was actually the most different of the other two, right? Case 2, case 3. Number 1 required us a little bit more detail to get to that relationship of the measure of the inscribed angle to be equal to half the measure of the arc it cuts. Um, and it wasn't just rinse and repeat that for case 2 and case 3. What we ended up seeing though is case 2 and case 3 ended up being corollaries of case 1, where remember corollaries are just basically instant consequences of knowing one other theorem. Then we know then these other two theorems will actually be true as well. And so, but again, case 2 and case 3 were also distinct because in case 2 we use the inscribed angle theorem for case 1 twice, and then we used addition. However, in case 3, we used it again twice, but then we used subtraction. So there were, again, 3 distinct cases as we reflect over those 3 cases for the inscribed angle theorem. We'll end off our lesson by looking at several examples, just applying the inscribed angle theorem. Let's take a look at our first example here. The measure of the arc BAC, so the measure of the angle BAC, which is an inscribed angle, is 25 degrees. Find the measure of arc BC, which means find the measure of the arc opposite of it. Well, what we just proved is that the measure of our inscribed angle, angle BAC, is half of the measure of the arc that it cuts, which the arc it's cutting here is the measure of arc BC. So now what you got to do is fill in what we know. Well, the measure of our angle BAC is 25 degrees. So now go ahead and solve this equation to get the measure of your arc. It's that simple. Just take that and double both sides, and we've got ourselves the measure of our arc. The measure of arc BC is 50 degrees. Let's do a second example. The measure of our arc BAC is 290. Find the measure of angle BAC. So notice that we're actually given the measure of arc BAC, which means we're going to go all the way around our circle from point B through point A all the way over here to point C. And the measure of that arc is 290 degrees. But we need to know the measure of the arc that our inscribed angle is cutting, this angle BC. This measure of arc BC. Well, in a complete revolution around our circle, we know there's 360 degrees. So if we know 290 of that lie with our BAC, our arc BAC, then what's left over for then our arc BC? Well, that would then be 70 degrees, right? 360 minus 290 is 70 degrees. So now we want the measure of our angle BAC, and we know the measure of the arc that it's cutting, the arc BC, which means we're just taking now half of 70 degrees. So we get the measure of our angle, our inscribed angle BAC, to be 35 degrees. Let's do one more example. You're actually going to see a couple corollaries of the IAT proven on your homework assignment. I actually prove one for you, and you're going to do the other one on your own. And in fact, the one you're doing on your own actually comes. It really is applying to this example here in our last slide here for our lesson. So what we're going to find, and I'll explain this to you in a little bit as we dive specifically into it. What we're going to find is that when you cut circles with parallel chords, there's an interesting result that happens. So let's take a look at our diagram below first. We have chord AB, which is a diameter, which means yes, this does pass through the center of our circle, and we have our arc CD, which is this arc from point C to point D, measuring of 40 degrees. What they're asking us to do is find the measure of this arc AD. We want to know what the measure of that arc is. So let's just call it X degrees. Well, here's what you're going to prove on your homework assignment. As it turns out, that if you have parallel chords cutting through a circle, they are going to cut arcs of equal measure. Meaning, since AB and CD are parallel to each other, that means the arcs they're cutting are going to be equal in measure. AD's arc is going to equal the same measure of BC's arc, which means BC will also have the measure of X degrees. Well, now we need to form some sort of relationship to find that measure of X. We'll go back to what we're given about the chord AB. It's a diameter, which means it does pass through the center, which means it has a straight angle, or rather the measure of that straight angle is 180. So the entire arc from A to D to C to B, the entire arc there, is a semicircle. And that semicircle also measures 180 degrees, which means we can add our 3 measures of our arcs together, and we can then solve for that missing measure of X. So we get 2X plus 40 is equal to 180. Subtract 40 on both sides, you get 140. Divide by 2 on both sides, you get X is equal to 70 degrees. And there we have it. There is our missing measures of the 2 arcs actually there, AD and BC. And so you're going to see that proof on your homework assignment, talking about these parallel chords. I do give you a hint of direction as far as how to actually prove this when you arrive to your homework assignment. So we've come to the end of our 9.4 lesson on the inscribed angle theorem. Please hop over and take a look at the 9.4 worksheet and begin working on that. If you do have any questions on that, do not hesitate to email me. With that, be good and do good.